So notice that from now on, whenever we write a chemical equation, we must label whether it's an elementary step or the overall reaction, because we're treating those quite differently. Well, I meant this to be an overall reaction. Nitrogen dioxide reacting with carbon monoxide. All right, so let's write down some possible mechanisms. Well, let's suppose that this happened in one step. If this happened in one step, what would the mechanism look like? If it happened in one step, it would have to look the same as the overall reaction. And yes, it was good that someone was asking about the phases. Well, logically, we have to keep the phases because they're part of what's happening. Remember that after all, sometimes you could have two of the same molecule, but just in different phases, and you can't tell that without that. Someone might have been remembering that we conventionally don't write the phases in half reactions, although we could, but that's not conventionally here. We should write the phases in overall reactions and in mechanism steps. It wouldn't be wrong to write them even in half reactions in electrochemistry. It's just a little bit less important or unconventional. Okay, so here's our proposed mechanism. By the way, this is what would be called some more terminology, an elementary reaction, if it's only one step. You can see why, because now the reaction is the elementary step itself. The reaction and the elementary step are the same, so it's called an elementary reaction. So here's one proposed mechanism. Another proposed mechanism. Now, before I forget here, maybe I'm now starting to see how the textbook is thinking about this. Notice that in this, they have these two NO2s, but they write them out separately. They don't write them as this, because they're trying to show that these two are reacting with each other. So we want to figure out which of these is the right mechanism. Let's introduce the idea of the rate determining step, which is a very important concept in physics. So this is a two-step reaction. So very likely one of the steps is slow and one of the steps is fast. And we want to know how does that affect the overall reaction. If one of the steps is slow and one of the steps is fast, well, should the overall rate depend on the slow rate, the fast rate, or a combination of the two?
Slow rate.
The slow rate by itself?
Yeah.
Yeah, that might be counterintuitive, but you don't combine these two rates. It only depends on the slow rate. That's a very important concept, so I can give you an analogy. Let's say that you like to take a walk every day with a toddler. So you go out with a toddler, and you guys have to stay together, so you can watch out for them. So you both have to be going at the same pace. Well, who's going to determine the rate at which you're walking, you or the toddler? The toddler, because they're a lot slower than you are, right? So what's the application of that? Well, suppose that you're getting frustrated with the slow pace of your walks, and you like to finish the walks a lot faster. How can you make those rates go faster? By adjusting what you're doing or what the toddler's doing. The toddler. So if you're frustrated with the slow rate, you're not going to be able to fix that by getting into better shape yourself, right? You can't set up a training regimen, start working out and getting better cardiovascular shape, and then hope that your walks are going to finish faster, because you're not the thing that's slowing you down. It's the toddler that's slowing you down. You have to get the toddler to walk faster. Maybe give them better shoes or tell them they're going to get ice cream at the end or something. But if you want to make the reaction go faster, you adjust the rate determining step. It's futile to work on the step that's already fast enough. Okay? Or the example that the textbooks often use are funnels. Let's say you have sand or liquid or something pouring through a funnel. Well, a funnel can have a bunch of narrow portions. This portion is narrow, and this portion is narrow. Let's say that you're frustrated that the material is not moving through the funnel fast enough. Are you going to be able to make it move faster by widening this portion of the funnel? Well, no, because this is not the rate determining portion of the funnel. This is the rate determining because this is where the biggest problem is. This is the point where, in a sense, the material has to move the slowest. If you want to, if you make this narrower, the reaction will go slower. And if you make this wider, the reaction will go faster. What would happen if I made this a little bit narrower? Nothing, because that wasn't the problem in the first place. Okay, so it's important to see that the overall rate depends on the rate of the rate determining step, the one that's the slower step. Okay. So, if you have a multi-step reaction, the rate of the overall reaction is the rate of the slowest step, and that's called the rate determining step. The slowest step is the rate determining step because of the arguments that we just made. Just like the toddler is the rate determining walker, or this narrow portion is the rate determining narrow portion. All right, now we want to figure out which of these is the correct rate for this overall reaction, like the scientist would actually do in the lab. Well, if this were the correct mechanism, what would be the correct rate law?
K times the concentration of NO2 times the concentration of Cl.
Good. Now, if this were the correct mechanism, first of all, what would be the rate law for the first step?
K1, rate equals K1 times concentration of NO2 times, you can put NO2 squared.
That's right, because we said that in this case there was really two separate molecules reacting with each other. So NO2 times NO2 is NO2 squared. And what would be the rate expression?
K2 equals, K2 times NO3 times Cl.
Okay, very good. But we still haven't figured out what the rate law would be for the overall reaction. We've just said what these two individual rates. It's just like what we've done so far is we've maybe figured out what, say, how fast the toddler is going and how fast the adult is going. But we haven't figured out the overall rate. Well, now we need to make an additional assumption. So far, without making additional assumptions, we don't know what the overall rate is. We need to assume who the rate determining step is, or who the slow step is. Well, let's start by assuming that this step is slow and this step is fast. How do I know that? Well, I'm just assuming it. Let's just suppose. If this were slow and this was fast, what would be the overall rate law?
The rate of the first step.
Just the rate of the first step. Just the rate law for the first step. Just like what's the rate of the pair of people walking? It's just the same as the rate of the toddler. The overall rate expression is the rate law for the slow step. We gave a couple of analogies to prove that. I'm going to keep calling this K1 for the time being because it came from the first step, although we could drop this if we're just focusing on the overall reaction. And now, how can we test which of these really is the correct mechanism, this one or this one, for the overall reaction?
Do experiments.
We could do experiments and figure out what the true rate expression is, like you learned to do last Friday, and then you could match them up against these. So let's say you do the experiments, and experiment shows that the overall rate law is this. If the experiment gives you that this is the overall rate law, which is the correct proposed mechanism?
Second.
We would know that the second is the correct mechanism, because if this was correct, or actually I should be a little bit more cautious, we know that this is not correct, because it doesn't match this. If this had been the correct mechanism, we would have gotten this rate law, which is not very close to this. Notice that, surprisingly, carbon monoxide doesn't affect the rate. even though carbon monoxide is a starting material here, it doesn't affect the rate of this reaction from our experiments. But if this was the correct mechanism, the carbon monoxide would affect the rate because it has to collide with the NO2. All right, on the other hand, this seems like a good proposed mechanism. Of course, we can't prove this is right. Maybe there's another mechanism that would also match, but this certainly seems a lot better than this. And in fact, we've also proved that in this mechanism, it looks like this is the slow step, or at least that would be consistent with the data. What if this didn't match the data and this didn't match the data? Well, we could try to come up with a new mechanism, or maybe we could try to figure out what would happen if this was the fast step and this was the slow step, and see if that matches the mechanism. We'll get to that in a couple minutes. So those are the different things we're going to be trying to go through. But it looks like we've matched this with the slow, we figured out this is the mechanism, or at least that's plausible, and this would be the slow step.